Hello, everyone. Um, Today we do section 3.2. There's actually going to be two videos today. The first one will be the lesson. It's explanation of a line of best fit, how to fit a line of data. We're going to do it like using the old-fashioned Algebra 1 way. And then the second video is going to be me showing you on your calculator how to find a line of best fit because it's pretty formula-oriented. So I figured two different videos, plus I don't have to bounce back and forth from my iPad to my calculator. So the object today, we've spent section 3.1 doing scatter plots. So now the idea is we're going to put a line on these scatter plots. So some of you have probably done this in a science class. Normally, if we were in a real class, I would do some stuff where we would have some little experiments and do some things and see which line is better, yada, yada, yada. But we're not going to do that. So I'm just going to show you. So the idea is we're going to try to put a line on data. Okay. So we have a bunch of data points like this one with a very strong positive correlation. And since there's a good relationship, there might be a reason to put the line on there, which we'll talk about in a second. So if you were in Algebra 1, what you would have done, I'm going to kind of walk really quickly through this. You would have kind of estimated the line of best fit. So we're going to learn in this section how to find what is called the line of best fit. Right now, we're just going to estimate it. So you put this line in there, and then you use some algebra skills to find the line of best fit. So what you would do would be something like this. Look, I drew this line purposely so it went through this point right there, that red point and that red point. So I'm just going to make up some numbers here. This is a little reminder. Let's say that first red point was the 0.27, and that second red point was the 0.813. Just ignore the scale for a second. All right, to find that line of best fit, we would find the slope first. 13 minus 7 over 8 minus 2, change in y over change in x, which is 6 over 4, which is 3/2. Then we would take that and write it maybe in point slope form, maybe in y equals mx plus b form. I'm going to put point slope form first and then change it. Or maybe not. Maybe I'll just do this. Y equals 3/2 x plus b. Then you pick one of those points and find b. So I'm going to put in the 0.27. So 7 equals 3/2 times 2 plus b. 7 equals 3 plus b. So b is 4. So I got this nice little graph. Y equals 3/2 x plus 4. So that's what you would have done in Algebra 1. We're not going to do that. You might have to do that one homework problem just to practice it. If you're eyeballing that line, you just make it go through those 2 points. It makes your life really easy. If it doesn't go through 2 points, then you have to kind of just estimate 2 points. It's all an estimation anyway. So then we would go through. But we're going to learn a method for actually finding the best line. Because if I actually gave you all these data points and asked you to do it, I'd probably get 5 to 10 different answers, right? You would all pick your own line of best fit. I might get 30 different answers. I don't know, but you might find those same 2 points. So that's just kind of the idea. We estimate the slope, we find the equation. We're going to do some interpreting in this chapter. The slope and the y-intercept will have some real-world application. So we'll talk about that a little bit. But what we're going to do is find the best line. So there is a best line. And by definition, it's called the least squares regression line. So if you hear me refer to the line of best fit, I mean the least squares regression line. The more technical term, of course, is least squares regression line. We'll talk about how to find it and how that works in just a second. But why do we need the line? We need the line to model or predict. We do this in science all the time, okay? So there's a lot of modeling and predicting that goes on. You see this pattern. Hey, there's a pattern. There's a relationship between x and y, so let's do something with that relationship. X is what we've called the independent variable in the past, and this one is usually called the explanatory variable because it explains y. It's also called the predicting variable because it predicts y. And then y is called the response. Ooh, not responsible. Let's get that out of there. How about, I'll just rewrite that, response variable. Might be responsible too. I don't know. So that's the basic idea of why we find a line. We do this in science all the time. And then we make predictions. There are 2 different types of predictions. The first one is called extrapolation, and the second one is called interpolation. We have this data set. So basically the idea is this. If you have a line, oops, let me start that over. Sorry about that. If you have let's just go back up to this one. If you have this line, if you make a prediction for any of these x values, in here, that's called interpolation. Your data goes from some x to some other x. Any prediction inside of that is called interpolation. If you jump outside the data, outside the model, it's called extrapolation. You have to be really careful with extrapolation. You can usually extrapolate a little bit, but remember, if this x value up here ended at 10, let's say, 0 to 10, and you wanted to extrapolate to 20, that's a little dangerous because we don't really know that this pattern would continue with all these other x's because we didn't test them. However, you'd probably be safe going to 11 or 12 because it's not very far, so you might think that model goes the same. So it just depends on what you're doing, what the context is. Sometimes you can extrapolate a little further, but you just don't want to go too far. Okay. So a couple definitions before we do the actual line of best fit is called prediction, a prediction error. So if you predict from an equation, okay, typically, if you have a point, think about this. If I have this line and there's some data points here, okay, this is the actual data point right there. But if you predict that data point using the line of best fit, you would get that orange point right there. Or maybe on this next one, if you predict this one, you would get that orange. So your prediction based on the line is not always the same as your data point. So this is what's called a prediction error. The prediction error is the difference, very simple, between the observed value, the point that's on the graph, and the predicted value, which is the one that would fall on the line. So a little terminology. We often use y hat. This is called y hat to mean the line of best fit. So this prediction error, kind of ignore my writing there. Sorry, this got a little messy. I'll do this. Prediction error, okay, is called a residual. And it's y minus y hat. And what that means is the observed value is the y, and the y hat is the predicted value. It's very important you do it in that direction. The observed value minus the predicted value. Anything that's above the line of best fit, the residual will be positive because the observed value is higher than the predicted value. Anything below the line of best fit is going to have a negative residual. Residuals become super important in finding the line of best fit, which is coming next. So I'm going to give you the formula for it, and then I'm going to pop over a second video just to show you how to do it on the calculator. So this is the formula. So when we put a line on data, there's lots of different lines you can put on there. So we say, which one's the best? So mathematicians have decided the one that's the best is called the least squares regression line. And the reason they call the least squares regression line is because if I have all these points, if you take all of the residuals, so remember the residual is how far away the point is from the line, y minus y hat. So all these little orange lines are residuals, okay? The line of best fit or the least squares regression line is the one, it's called the method of least squares also. It's the one that minimizes the sum of the squared error. So if you take all those orange lines, square them, don't add them up because some are positive, some are negative. So clearly, if we want to add them together, we want to get 0, right? But it turns out there's actually multiple lines that will get you 0, but some are better than others because of this next step, which is if you take the positive distance, in essence, you square it and add them up, it's the smallest one, okay? So that's the idea of what a least squares regression line is. We're going to learn how to find it. So here are the properties of least squares regression line. The first one is that the sum of all of those residuals will be 0, which also means the average will be 0. Hopefully that makes a little bit of sense. That would be the perfect situation, right? You get the same amount above as you do below. So the residuals add up to 0, but like I said, there are multiple ones. So there are other properties. The second property is just the variation in those residuals must be as small as possible. That's the idea of squaring them, adding them up. How do we find that? Well, it turns out also that line of best fit will always contain the point of averages. There's a little X bar and Y bar missing here. Sorry about that. X bar, Y bar. So if you find the average of all the X values, and you find the average of all the y values, that point will be on the line of best fit. It's a pretty important idea because it helps us write the equation. All we need is the slope, right? Because remember, that's the whole idea of a line, is a slope and a point. So once we have the point, we need the slope. And here's where it gets a little complicated. This formula is not a memorized formula. You do not have to worry about memorizing it. But it's on your note sheet. This is the formula for slope. In statistics, this is going to confuse you just a little bit. B1 means slope, not y-intercept. I know in algebra, you're used to B being the y equals mx plus b, the y-intercept. In calculus, we don't use statistics, we don't use m. We use b. It came beforehand, actually, believe it or not, it changed. So the formula is you take, and I'm going to walk you through this on the calculator, or on the next video on the calculator, but just the idea is you take every x value and you subtract the mean. You do this for every x value. The corresponding y value that goes along with it, you subtract its mean. So you take a point, okay, you take a point and you subtract the x value from the x average from the x, the y value from the y, and you multiply them together, okay? Once you multiply them together, you're going to add them all up, okay? And then you're going to divide that by each x. So when I say x, that means x, those are the same x. So you just do it for every x. And this will make a little bit more sense on the video, the next video, the calculator, just so you can see it. The problem is if there's a lot of points, it takes a lot of work. So I'm going to show you a nice little kind of shortcut way on the calculator. So that's the formula for slope. So what you would do is you first thing, and I'll do this on the video also, you find x bar, you find y bar, okay? Then you do all this formula to find the slope with all the points. Now once you have the slope, okay, then you find the slope. Once you find that slope, now you have the slope and a point, because remember that x bar, y bar is on the graph. You can't pick any point in the data set because those aren't necessarily on the graph. The only one we know for sure is on the line of best fit is the point of averages. So once you have the slope and the point of averages, you can do. So the next video will show you how to do this. It's the big part of this chapter, actually, or section. So, I mean, knowing what it is super important, but how to find it on the calculator, it's a little bit tricky the first time. So hopefully you'll pop back right over to that other video, and we'll see you in a second.